Theorem of calculus. So it's a big lengthy thing, and you'll come to realize it's something we've already been using anyway, so it's really nothing new. So it's actually a two-part thing. The first part has to deal with integrals. So in order to be able to take the antiderivative, we need our continuous function between 2 points. And if we are looking at this, you'll notice that there is a variable difference. We're saying g of x is equal to the integral from a to x of f of t dt. Okay, so if you integrated f of t dt, t is the variable here. So you're going to do the antiderivative in terms of t. But then what happens is if x is a variable and a is a number, once you plug those in, you're going to get another function minus some number, right? And that is the function g of x. So they have this big lengthy thing in the book, which is basically just talking about if we integrate how one variable can get switched to a different one, if I have a variable as my limit. So if we think about it in terms of areas, if this blue curve is my original function f, then we can use the integral from a to x to represent the area from a starting point A to wherever x might be. And so instead of just giving you two numbers that you have to then calculate the area, so maybe from 1 to 5, and then I said, no, I want from 1 to 7 now, and oh, I want from 1 to 10 now. Instead of having to restart every time and do the antiderivative again and again, you could do it one time going from 1 to x, get an equation with x in it, and then when I give you all these different endpoints, you could just plug those in. So it's just basically giving you a formula for finding area under a curve. So we're going to start with an example that's going to use a little bit of approximation to kind of understand this concept. So f is this blue graph here. G is the integral from 0 to x of this function. So we are going to find all these different values. G of 0, G of 1, 2, 3, 4, and 5. And then we're going to use those to graph G. So the function is f, but if G is equal to the integral, an integral means the area under the curve. So when I say the G of 0, I'm saying the area under this curve. We are starting at 0 and ending at 0. What happens if you start and stop at the same point? What's your area? 0. All right, when I say G of 1, I'm asking you to integrate from 0 to 1. So if I start at 0 and I end at 1, it's saying, tell me, what's this area? All right, so we could kind of think of it. We don't have the equation of it, so we have to estimate, right? If I swung this little rectangle or triangle down here, it would pretty much make a full rectangle, right? Here's the rectangle length times width, so 1 times 1 is 1. It makes one full box. Okay, G of 2. So we already have 1. If I throw in 2, how much more am I adding to it? 2 more. So now our area is up to 3. If I said G of 3, so we're at 3. Now we have to say, okay, how much more would this add in? We're going to have to approximate. It's definitely more than 1 full box, isn't it? So what do you think? Like 1.3 is probably not 1.5, because this is about half of 1, not quite a full one. So you want to say like add another 1.3, so that would take us up to 4.3. Does everybody know how I'm getting my numbers? What happens when your areas are below? It's negative. So would you guys agree this amount is about the same as this amount? So if I subtracted those off, what am I back to? 3. G of 5. So that looks like I'm subtracting the same amount again. So we've been calling that like a 1.3. So if I have 3 and I subtract another 1.3, it would take us to 1.7. So then if I wanted you to sketch a graph of G. So the next slide I gave you a blank grid. these are just like ordered pairs. First point, 0, 0. And we had 1, 1. G of 2 was 3. G of 4, G of 3 was 4.3. G of 5 was 4 is back to 3, and at 5 we had 1.7. All right, so some kind of graphic question. I don't really know how curved this is, how straight it is. We don't know like concavities or anything crazy like that. But we just have some general values. So we just estimated what this curve might look like. So this curve, this graph is representing the area under this original function. Any questions there? So the fundamental theorem of calculus, part 1, tells us if you have a continuous function on the interval a to b, so continuous means we can do the antiderivative, and x is somewhere between it, then the derivative of g is equal to f of x. So g is the antiderivative. The original function was f of t, right? If you do a derivative and an antiderivative, you should get your original function back. What happens is if I'm doing this and my variable, I have a variable in my limit as an x, when you do the antiderivative, your t gets turned into an x, and then once you do the derivative, x stays. So the derivative of g is just f of x, so it just changes the t's to an x. Not an overly, not something we're going to use a ton of, but it does have important implications later on, so we can't just skip over. Okay, so if I ask you to find the derivative of this, we're going to do it 2 different ways. You okay?
Yeah, I rubbed my eyes and I forgot I was wearing this myself now.
Now you're gonna cry.
Oh no.
All right, so if we work it out, okay, if I ask you to do the derivative of this integral, first we would have to integrate it, right? So what is the antiderivative of t squared? No, that's the derivative, antiderivative. Plus, what is the antiderivative of 2t? Plus, antiderivative of 1? T. And we're doing this from 3 to x. So if we plugged in our x's, 1/3 x cubed plus x squared plus x, minus plugging your 3's, 1/3 times 3 cubed plus 3 squared plus 3. Okay. 3 to the 3rd is what? 27. Divided by 3 is 9. 3 squared is plus 3. So the antiderivative is 1/3 x cubed plus x squared plus x minus 21. Now, what am I asking you to do to that? We need the derivative. What is the derivative of this function? X to the 2nd plus 2x plus 1. So we worked that one out. We did the antiderivative, and then we did our derivative. The fundamental theorem of calculus says if g is equal to the antiderivative, g prime, the derivative of this, essentially just cancels out the integral and changes our t to an x. So if I want to use the fundamental theorem of calculus, it's basically saying, okay, that goes away, but all my t's turn into x. And we would get x squared plus 2x plus 1. Is that the same thing as when we worked it out? Yes. So all it's telling us is a derivative and an antiderivative, they're inverses. They cancel each other out. So you're always going to get the original back. The only difference is because I had a variable in my limit, my variable changed within my function. Any questions there? Mm-hmm.
So whatever the variable is in the integral, which will be a variable in the function.
Mm-hmm. So if it were a z, they would all change to z's. So if I asked you to find the derivative of this, can you just tell me what it would be equal to? So just be the square root of 1 plus x squared. Now you could certainly do the antiderivative and then do the derivative of it. But if we know that fundamental theorem of calculus, it saves us. It does require that the function be something we could, that the original function is differentiable. So remember, differentiable, it has to be continuous, it has to be defined. So that is something we should recognize here. Square roots, you know you have to have positives underneath, but if you square something, you always have a positive. So it's always continuous and defined. Square root doesn't have breaks in the graph. So we can use the fundamental theorem of calculus.
So if it's not continuous or defined,
We cannot do the fundamental theorem, so we'd have to have some other options or work it out. If it's not continuous, we would have to be making like multiple functions and evaluating or doing something like that. All right, if I ask you to find the derivative of this. So, I'm not asking you to do the fundamental theorem of calculus because what did I change? Instead of just an x, I put an x to the fourth. So I want to work this out and see if we can figure out a pattern for that. So if I wanted you to work it out, first we have to do the integral. What is the antiderivative of 2t? T squared minus antiderivative of 3. And we're going to integrate that from 1 to x to the fourth. Right, so if I plug in my x to the fourth, I get x to the fourth squared minus 3 times x to the fourth minus, if you put in a 1, 1 squared minus 3 times 1. 1 minus 3 is -2, so minus -2 makes +2. Okay, then what do we have to do to that? The derivative. What is the derivative of this? Minus 12x cubed. Okay, so that is the final answer. Is there any way we could use the fundamental theorem of calculus here? So when we have just an x, all we have to do is change those to x's. Is this equivalent to me just plugging in an x to the fourth? No. if I rewrote this, if I factored, what's my greatest common factor? 4x to the third. If I took that out, I'm left with 2x to the fourth minus 3. 2x to the fourth minus 3, is that the same as just plugging the x to the fourth in here? How is 4x cubed related? It's the derivative of x to the fourth. So if it's not just a plain x, you can do the same thing. You can plug it in, but then you just have to take it times the derivative of that number. All right. So let's try one of those. If I asked you to find the derivative of this integral. So derivative and integral, they kind of cancel each other. We had secant of t, my t would turn into x to the fourth, and then what would I have to take it times? Times 4x. Is that okay with everyone? Okay, the second piece of the fundamental theorem of calculus is the one that we're really worried about, and it's the one that we've already been using. We just didn't have a name for it. So we've been doing integrals, and we know when we integrate, we do the antiderivative. If we evaluate, we do the antiderivative of the upper limit minus the antiderivative of the bottom limit. That is actually the second part of the fundamental theorem of calculus. So nothing new, we've already been doing this. So we're going to continue practicing these integrals because in the coming sections we're going to get to some more complicated ones, so we're just going to keep practicing these skills that we already have. So if I asked you to evaluate this integral, what is the antiderivative of e to the x? E to the x, and we're evaluating this from, so what do we get for our answer? E to the third minus e to the first. So this one, if I want the area under a parabola. Area under a curve is the same thing as asking you for what? The antiderivative of x squared from 0 to 1. So why don't you guys work that one out for me? So we're just going to integrate from 0 to 1 of x squared dx. Antiderivative of x squared, 1/3 x cubed, from 0 to 1. And did you guys get 1/3? We're going to do just a couple more and then we'll stop for today. If I asked you to evaluate this integral, you could rewrite this if you wanted. Dx over x is the same as saying 1 over x dx. What has a derivative of 1 over x? So we get the natural log of 6 minus the natural log of 3. Alright, bonus question. How do you put those natural logs together? Logs are subtracted. What do you do with their arguments? You divide. Think about it's like exponent rules. You subtract exponents when you're dividing. So it's the same thing as the natural log of 2. All right, 2 more. We have to figure out what makes x cubed plus x equal to 0. Sorry, minus x. So you could take out an x squared minus 1. What makes that 0? Okay, so that means we have to go from negative 1, because that's our starting point, to 0. Then we'll have to go from 0 to 1. And then we have to go from 1 to 2. If you plug in something between negative 1 and 0, so like negative 1 half. Negative 1 half cubed minus negative 1 half. That would be a negative 1/8 plus 1 half. Is that positive or negative? Okay, so the absolute value doesn't change anything there. So that part will just remain x cubed minus x. If you do between 0 and 1, so like positive 1 half. 1 half to the third is 1/8 minus 1 half. Is that positive or negative? Negative. So the absolute value would do the opposite of it. If you go between 1 and 2, so like 3 halves. 3 halves squared, cubed, would be 27 over 8 minus 3 over 2. Right. 3 over 2 is like 12 over 8. 27 minus 12 is positive. So this part, nothing changes. So now we do the antiderivative. Antiderivative of x cubed minus antiderivative of x. These from negative 1 to 0. Alright, this one would be a negative 1/4 x to the 4th plus 1 half x squared. Start with this one. 0 to the 4th is 0. 1/4 times 0 is 0. Minus 1 half times 0 is 0. Negative 1 to the 4th is 1. 1 squared is 1 times half. Next piece. Put in a 1. Negative 1/4 times 1 is negative 1/4 plus 1 half times 1 is 1 half. Minus, if you put in zeros, we get 0 plus 0. Next piece. 2 to the 4th, 16 times 1/4, so 16 divided by 4 is 4. 2 squared is 4 times a half is 2. Then 1, 1/4 times 1 is 1/4, minus 1 half times 1 is 1 half. So now we just have to clean this up. We don't need calculators. We can do this. Shame on you people. You don't need it. This is 1/4. 1/2, that's like 2 over 4. 1 over 4 minus 2 over 4. Negative 1 over 4. So minus a negative makes positive 1 over 4. Okay, this is negative 1 over 4 plus 2 over 4, which is 1 over 4. 4 minus 2 is 2 minus 1 over 4 minus 2 over 4. That's a negative 1/4, so minus a negative is 12. Okay, 2. That would be the same as 8 over 4. So 1 plus 1 plus 8 plus 1 is 2. 11 over. Look at us doing fractions without a calculator. Quit glaring at me, everybody. It's not that bad. You did it in 6th grade. You can do it now.
We skipped over that section.
Oh, you did not skip that section. That's like half of the year. Okay. Last problem of the day. Find h prime of x if h of x is equal to this integral. So, h prime, what does that tell me? We need the derivative of this. All right, so what can we do? Yeah. All right, we can do the fundamental theorem of calculus. We replace all of these t's with x squared. And then, since it's not just a plain x, we also have to multiply by derivative, which is 2x. Okay, x squared cubed would be x to the 6th times 2x will give me 2x to the 7th times the sine of x squared. All right. Monday, we are going to finish this section. Homework, you can really probably do probably close to the whole thing, if not all of it. But we're going to be practicing some more of the ugly integration problems, and we'll do some initial values.